You have lenses and mirrors in optical sensors gives you some capabilities you don't have in electromechanical or capacitive sensors, because using a simple lens you can make the sensing area bigger or smaller or farther, and using mirrors you can sense around corners and things you cannot do with normal electromechanical sensors, because you can sense the light wherever you want to with mirrors, and you can sense from a distance. So the optical sensors are much more flexible in what you can do with them. And I gave you an example, which we're going to repeat, that you can separate the variables in an optical sensor very elegantly. So I just want to repeat this example, that if I have a split detector, which is the thing I showed you with two detectors and a meter measuring the difference, if I have a split detector and I want to measure in one case angle and in one case position without being affected by the other variable. So this is the classic split detector. I'm getting here A minus B, typically through an op-amp, okay? Doesn't have to be connected that way, I'm just showing it a differential connection. In real life you actually will connect both to the negative. One is just be wired reversed. From point of view of electrical design it has advantages. Okay? So, and if I put a lens, so if I put a lens which is focal distance away, f away, any parallel beam will reach a focus here, and if the beam is not exactly parallel, like the beam from an LED, it's okay too. It will reach almost a perfect spot here. So if I have a beam like this, which is, I'll draw it this time not so parallel, because let's say it's coming from a lens and an LED. Okay, this, because this is large distance. This is, L is much larger than F. So this will come to a spot, maybe not perfect, because this is not a point. A point can come to a point, but this is not a point, so it's not going to come to a point, but something like this. Now, if I move, so this is the central axis, okay? Now, if I move the LED sideways without changing the angle of the central ray, if I have different central rays, because this is at focus, they'll come to the same point. If it's a laser, it'll be exactly the same point. If it's collimated, but LED will be close. So parallel shift is not going to make a difference in the reading, but if I tilt the angle, if I take this thing and I change the angle, so the central ray goes at a different angle, okay? So let's say if I can take the central ray and bring it at a different angle, so this will be the central ray, it will end up at a different point, because the central ray acts as a pivot around the center of the lens. So the central ray doesn't bend, it just tilts. Okay? So this way I can be not 100% immune to displacement, but largely immune to displacement, only see angles. With a laser it's much more clear. If I put here a laser, tilting will just move the central ray, move the spot, shifting will do nothing. Now the inverse of that, now I have the same situation and I want to do the opposite. So I have the same detector, A and B, A minus B, but now I want to measure only shift. So there are certain ways to do it. Actually, the simplest way to do it is place the lens to be imaging the LED. So this is your same LED as before, but you place the lens, so this is U, this is V, and like we talked Tuesday, imaging meaning 1 over U plus 1 over V equals 1 over F. So this forms an image of this. So let's draw it here. Say the rays go like this, and it will form an image. You'll see a little image of the LED here. Okay, the nice thing about imaging, that if I send other rays, say if the lens was bigger and I send other rays, all the rays will end up here, because imaging means that a given point here sends out many rays, but all these rays end up at the same point here. That's what imaging means, okay? So now if I tilt it, it is just the same as selecting different rays, which don't matter, because the point which is the source of these rays is still here. Okay? Is that clear? So if I'm imaging, the point can have many rays. Not all the rays will be captured by the lens, but all the rays captured by the lens will end up forming the same point here. So tilting it would make no difference. But if I move it, if I move the LED to here, if I move the LED to here, obviously the image will show up here now. Because imaging, if I move the LED, imagine you had two LEDs, so you'll see two LEDs here. So moving the LED is going from LED 1 to LED 2, so obviously that image will move. Okay? So in this case, if I can image, I'm 100% insensitive to tilt, and I'm exactly 1-to-1 only sensitive to position. However, again, I'm a bit sensitive to this position as well. Because if I move this in and out, then I'm going out from perfect imaging conditions. So all the thing I say immune to means to a great degree. Right? Because when I say I want this to be angle but not displacement, if I move it in and out, I'm still slightly sensitive to displacement because the angle of the central ray changes. So if I move this LED to here, the angle of the central ray will change. But the effect is reduced. Now, there is in some conditions, you can design optical sensors which are truly immune to the factor you want, but you probably need more than one lens and some more tricks. But even with a simple lens, this is an angle to measure. This is a sensor to measure angle, and this is a sensor to measure delta x, and they have quite a high immunity to the non-measured variable. Okay, so I think your imagination can fill up the rest, what you can do with optical sensors. But there is a general question. So far I said all the good things about optical sensors, so you can do a lot of tricks with them, a lot of flexibility. But there is one thing about optical sensor in terms of immunity to interference, which we didn't see in capacitive sensors and in inductive sensors. So what kind of interference, if I set up an optical sensor in this room right now, like I did Tuesday, what kind of interference would I get that I didn't get when I set up the LVDT or capacitive sensor? So what do we have plenty in this room which can interfere with an optical sensor? Light. So think of it, everything is fully lit. So if I have an optical sensor and I put my hand and put a shadow on it, I will affect the balance between A and B. Now, if I took a photocell in this room and connected it to a scope, to an oscilloscope, what will I see? Say if I have an oscilloscope and I connect a photodetector and I look at what will the light in this room look like on an oscilloscope? Yeah, go ahead, please. Okay, so we hear one answer. If this is 0, it'll be a steady offset from 0. Okay? Obviously you never tried it. But it's a good first guess. Okay, so, and other guesses? Yes?
Maybe at a specific frequency, like 60 hertz or something.
So you're saying 60 hertz what? What will I see? A sine wave, a square wave?
Yeah.
Sine wave at 60?
A lot of noise on it.
Yeah, a sine wave at 60 hertz with some noise on it. Obviously you haven't tried it either. Okay. Okay. So has somebody ever actually looked at a scope on a photodetector in their whole life? That's very bad. Because you're going to graduate in a year or two and none of you ever actually looked at a photocell, what you see. So, a bit more imagination. Yes?
Noise? Random?
Why would you see so much noise? The room is closed, the light is steady. You see some noise, but the primary factor you see is not noise. Yes?
Maybe a sine squared wave.
Ah, okay. So obviously you didn't try it either, but at least you were more imaginative. Okay. So you're saying you'll see a sine squared wave which looks like this. A sine squared wave is actually a wavelength that doubles the frequency, right? It's this. Okay, but that's not what you see either. Okay. Okay. The answer is very simple. Okay. The fluorescent lamp makes light equally when the polarity is A or reversed. The power to the fluorescent light is, of course, a sine wave at 60 Hertz. Now, the fluorescent light doesn't care if the current goes this way or this way. So what it does a rectified sine wave. Now, a rectified sine wave, as you know, is not a sine squared, right? So that's what the light looks like in this room. Okay? And that's a big problem, because anybody, and usually it sits on some DC. It sits on some DC because in this room we also have a projector and this light comes from rectified DC. Like the projector light comes from a xenon lamp, which operates on rectified DC. So there is a background light, sometimes sunlight, not in this room, but there is some sunlight, okay, some projector light, and a rectified sine wave, which means a frequency. If you look at this waveform, the fundamental frequency is 120 Hertz, not 60. So what you get, and if you're more mathematically oriented, you actually get here, you will get simply a sine of 120 Hertz, okay? But this is not a sine of 120 Hertz. This is because it's a rectified sine wave, it is a set of Fourier terms, right? And you'll get actually all the multiples of 120 Hertz. Okay? At least you'll get here only the even multiples if you want to be really more accurate. So here you'll get 120 Hertz, 360 Hertz, and so on. Here you'll only get 120 Hertz. Okay? Okay, so that is not so good, because if I have an optical sensor, and even if the signal of the LED is strong, there's strong lights here, and if I want to make a sensor to 0.1% or 1%, even if the LED is 100 times more powerful than the room light, I still get an error. Okay, so what do you do about it? And not just about it, what do you do about the problem that if you have an optical sensor, you move it out to sunlight, suddenly you get a huge DC. So obviously optical sensor, unless it's enclosed in a box, is very sensitive to light leaks. So I know here you will say this is AC, I can filter it out. But it doesn't help, because you can take it out in sunlight and then it's DC. So the problem of all sensitive optical sensors is, what do you do to prevent them from being affected by ambient light? So some ideas. Yes, please. Pardon? Okay, first answer, shield it. You try to cover the light path, put a shield around it, and that's good. But sometimes you want to debug the sensors, you have to open the cover to work on it, and then what do?
You have a photo cell open to just the ambient conditions, and then you subtract it from it.
So that's basically not a reference sensor or differential, but it turns out we are doing it already. Because if you use a differential sensor, we are already doing what you suggested. Because the ambient light will hit both sides roughly the same, and it will be cancelled out. Okay? But as I said before, if I put my hand and shadow one side, or objects move around me, and then the light is not exactly the same on both sensors, which can happen. Let's say light comes from one direction, so one sensor is closer to the light source. So the first order is taken care by going differential. And that's why an optical sensor, you pretty well must go differential, because the first order is cancelled by this. Same as any differential circuit, which we talked many times. But what do you do with the second order, like in kind of uneven lighting? Shadow, uneven lighting, especially say you have a projector in the room, you have a projector which projects a movie. You can have part of the movie here and part of the movie here, right? So constantly you have changes in the light. So there is two standard techniques, which are basically is no different between optical sensors and other sensors. There's two standard techniques, which one we dealt with already when we talked about LVDT, and the other we haven't dealt with. So we said in an LVDT there is some advantages that it's running on AC, but we can artificially create these advantages. So what would you do? Speak up. Normalization we are already doing. Well, we are not doing here, but we're doing anyway, because to keep it insensitive to the amount of light. All these sensors are normalized. I don't even mention it. But I mentioned, when we talked about LVDT, I said the fact it's on AC, running on AC, not on DC, is actually an advantage, not a disadvantage. And I explained why very briefly. Yes? Drift. And what did we do about it? So in noise reduction and drift, what we can do is put a filter. And the filter can be tuned. Okay, but here we have DC, so we can't put a filter. But LEDs are very, very easy to modulate. So now it opens up a possibility. Instead of using DC sensor, I can put in a modulated LED. And the LEDs can be modulated up to quite a high frequency. Does somebody have a guess up to what frequency can an LED be switched? Just order of magnitude. Megahertz is a good answer. An LED roughly can be switched to a megahertz, so I can modulate this light very, very fast. Megahertz probably will need a much better amplifier, but I can put 100 kilohertz. And then I can put a bandpass filter here. So what I'll do now, instead of putting DC, I'll modulate the LEDs at a high frequency. I wouldn't do it at 100 hertz or at a kilohertz, because then I may still hit a harmonic of that. Remember, we said this is a nasty waveform, has harmonics at 360, which is a third harmonic, has harmonics at 600 hertz, which is a fifth harmonic, and goes on and on and on. Okay, and if it's a bit distorted, it will start getting also even harmonics. Okay, so here, but the harmonics get smaller and smaller. When you look at this, when you look at the Fourier series of, say, a rectified sine wave, you get the fundamental at 120 hertz, and then you get this, but eventually it dies out. So if you go 100 harmonics away, you ignore it. Okay? So I wouldn't go near hertz, maybe not even kilohertz, because I still may run into some harmonics, some noise, but a good number is, say, 100 kilohertz. Op-amps still work very well at 100 kilohertz. I don't need a special amplifier. So I'll modulate it typically 10 kilohertz to 100 kilohertz, unless there is a special reason to go to some exotic frequency. Okay? And then, of course, here the signal will be AC. Okay? It will actually be like this. Again, even when I modulate, depends how I do the modulation on the LED. I can modulate it like this, modulate it like this, but it doesn't really matter. So it depends if I put a DC bias on the LED and change the current, or I just pulse it. Okay? But now I can put a bandpass filter. Now I can put a bandpass filter here, where this is F and this is amplitude, and the bandpass filter can be tuned to F. I'm using F for frequency and F for focal length, but obviously you're not going to be confused by that. Okay? So I'm using on the same drawing, unfortunately, but I'll just say F hertz, so it's clear. Okay, so I put a bandpass filter, and now you're already a lot smarter, and you know that the width of that filter cannot be 0. It has to be a certain width. Even if that frequency is perfectly stable at F, the filter has to have a certain width. And this is why we covered it on the LVDT. Exactly this drawing. So why does a filter have to have a certain width even if the frequency is spectrally pure? Information content. And again, we'll talk one more time about it next month, but that's your last chance. After that, you better remember it. Okay? Because when I move the LED, this becomes amplitude modulated. So the signal coming out, as the sensor is tracking movement, looks like this, where this is a movement. The envelope is a movement. But this is an AM signal, amplitude modulated signal. And an AM signal, when you look at its spectrum, it doesn't just have a carrier. An AM signal has a carrier with a bunch of sidebands, and this carries the information. It's the same when I speak on the radio on an AM station. If I don't speak, I just see a carrier. But if I speak, all kinds of sidebands appear, and this, of course, are the contents of my speech. So if you have a zero width filter, only the carrier will come through and there will be silence. Okay? So this has to be a certain width. As I said, we'll cover it more time. This width is not much, maybe 100 hertz or kilohertz. And now I'm immune to all light, sunlight, room light, pretty well immune to all light. So you do two things. One thing, you use modulated light, or modulation. Okay, and there is a second trick, which is like secondary trick you should always do when you have a system. There is a rule: if you design a system, you always put in a filter somewhere in the system which limits the bandwidth to the bandwidth you need. Now, most inexperienced people don't do it because they say, who cares? If the system has more bandwidth, who cares? But you don't do that. In any good design, you always put in a filter. Say, if you need the system to work at 1 kilohertz, put in a filter at 2 kilohertz. You don't want to be marginal. You don't want the filter to start cutting your signal. But in every system, it doesn't matter if the system is mechanical, hydraulic, electronic. It's easiest to do in electronic or optical. You don't let the system have more bandwidth than you need. And there are some reasons for it, especially in a servo system, because we said if the system has too much bandwidth, there's more chance to oscillate, because the higher the bandwidth, the more chance that at some frequencies there will be enough phase shift to cause oscillation. It also picks up more noise than you need, because noise typically has a kind of broad spectrum, so if the bandwidth of the system is wider than you need, it just picks up more noise. There's a long list of reasons. The third reason is aliasing, which I'm going to talk about next month. So there's many good reasons why you always want to limit the bandwidth of a system a bit more than you need, not to be marginal. And again, I wouldn't get any further into it right now. But the same thing is true for an optical system. So this is modulation of the light, but the light itself is a sine wave. So what this shows, this graph, is the light intensity changing. But even if the light intensity was not changing, the light itself is an oscillation which has a frequency which dictates its color. So if I put in a red LED or a green LED or a blue LED, each one of course has its own oscillation which is many, many orders of magnitude higher than the oscillation I make it blink. Okay? To give you an idea, the light itself, if I talk about roughly, if you had to guess what is the frequency of the light itself, can you throw a number? Is it megahertz? Is it gigahertz? What is it? Well, it's easy to answer, because frequency is simply the speed of light divided by the wavelength, just like any wave. So you have 3 times 10 to the 8 meters per second, divide, and let's put green light, because green light is like the middle. It is 0.5 times 10 to minus 6, because green light is 0.5 micron meter. Okay? So if I divide it, I get 6 times 10 to the 14 hertz. Now, so that's 600 terahertz. You may have heard of gigahertz, there is terahertz, like they use in airport, terahertz imaging, but this is 600 terahertz. So the actual wavelength of the light itself is so high that you don't even want to think of it, because there's nothing you can do at this frequency electronically, but you can do things optically. Okay? Because any piece of colored glass is an optical filter for those frequencies. So again, to recap, if I want to filter the AM using electronic filters, let's say I modulate this at 100 kilohertz, I want to filter out electronic kilohertz, so I take an op-amp, make some active filter, or take an LC and make some tuned circuit, okay? But if I want to filter the frequency of the light itself, I can't do it electronically because it's 600 terahertz, okay? So I have to use optical filters. So optical filters means just pieces of colored glass, or what's called interference filters, that I wouldn't get into right now, but I will mention when we talk about interference. So there is 2 levels of filtering. The first filter I can put in is an optical filter which lets the sensor only see the color of light that the LED comes out with. And especially if this is a laser, the spectrum of light of a laser is very narrow. Now I'm talking about the optical spectrum. Okay, so now if I draw the spectrum, optical spectrum, I look like this. So this is amplitude again, and this is optical spectrum in terahertz. Okay, but many people prefer to show it in a different scale, actually show inverse, show the lambda, which in optical terms, it's easier to talk about the wavelengths than the frequency. So one is just the inverse of the other. So a laser will look like this. So say the green laser pointer I have here is a clean spectral line at 532 nanometer. The red laser pointer that most of you have is a clean spectral line, depending on the laser diode, at typically 650 or 635 nanometer. But they're very clean lines. Now the modulation, the AM, doesn't affect this, because here the thinnest line you can draw on a terahertz scale will be many megahertz wide, right? So the modulation caused by moving the sensor is negligible. So now I can put a very narrow optical filter. I can put an optical filter which is as narrow as I can make it, and I'm not worried, because there's no issue with AM or information, because the narrowest optical filter, let's say, will be 0.01 nanometer, the kind of filters they use in telecom. And even this gives you gigahertz of bandwidth. So the answer is you use two-level filtering. The first thing you do, you put an optical filter. So the optical filter, you just put a big piece of glass in front of the detectors. And this is called band pass filter, but of the optical type. And this is matched to the color of the LED or matched to the color of the laser. If you use an LED, it looks a bit different, because an LED looks like this. Okay, so I'll just redraw it in a clean way so you can copy it. So an LED is not a perfect zero line spectrally. It has a certain bandwidth in nanometer. In other words, the color isn't so pure. So can somebody guess, if an LED says on it 500 nanometer, what bandwidth optically does it have? Is it 1 nanometer, 100 nanometer? Okay, so the answer is in the order of 50 to 80 nanometers. So when you buy an LED, and now I'm going to use the lambda scale instead of the F scale. So basically it's an inverse scale. This is the highest frequency, this is the lowest frequency, because we're using wavelength scale and amplitude. So an LED, say if this was 500 and I bought a green LED, 500 nanometer, it would be about 50 nanometer or 70 nanometer. While a laser, if I bought a green laser, it would be perfect. But the filter doesn't have to be exactly like this. A filter could be any filter which lets most of the light through. Or could be rounded filter, any filter you can get. So if you use a green LED, you put a green filter, okay? And then, so you filter first the light, and then you put a second filter here, which actually filters the modulated light, and this filter here is tuned to the modulation frequency. So to redraw it, if I have an optical system which has an LED or a laser shining on some detectors, some lens, and I have an amplifier, I'm using two bandpass filters. One bandpass filter is an optical bandpass filter, and this is matched to the color of the light. Okay, so it's basically a piece of colored glass. Okay, matched to this, and then I use an electric bandpass filter which is matched to the modulation frequency. So this is typically in the kilohertz range, and this is colored light, which means in the hundreds of terahertz range. Basically, here we really talk about it as color, not as frequency in the visible. Okay? So is that completely clear how I reduce ambient noise with two-stage filtering? Good. Now, so anybody who designs this, anybody who designs a sensor like that, uses a green LED and a green filter, you immediately can see the person is totally inexperienced in optics, because the green is not the right color for optical sensing. Red is. Red or infrared. Now, can somebody explain why? So basically, if you build a sensor like this with a white LED, a green LED, a blue LED, it means you really don't understand optics. You should do it with red or infrared. Okay, now can somebody explain why? Yes, please. Okay, the first thing, the peak of the ambient light is green, because the human eye was developed by nature to peak in green. So all these lights are trying to maximize the green, and also sunlight peaks in green, and that's why human eye was developed to peak in green, right? That's why plants are green, because they are matched to the sunlight. Because, you know, the spectrum of sunlight looks something like this. Okay, well, it has a lot of infrared, but basically, if I draw spectrum of sunlight on this scale, it will look like something like this, but it peaks in the green. That's just black body radiation, right, as you remember from physics. So because of this, all the plants developed to be green, and human vision peaked in green. Okay, so there's a lot of ambient light in green, but if we build a sensor, we don't like it. But that's not a big difference, because the amount, if I look at green or I look at red, the ratio is less than 2 to 1 in ambient light and in human sensitivity. But there is something else, which if I'm smart, I don't choose green for sensors, which is more important. Yes? Beautiful, beautiful. Because what really matters is not the peak of our vision. What matters is the peak of the sensor's vision, which may be very different and depends on the sensor material. So now, if I take silicon and measure it, how does silicon respond? So this was like 0 nanometers, and say this was, say, 1 micron, 1,000 nanometers. So this was an LED, a green LED. But if I take on this graph and plot silicon, silicon looks very different and actually looks like this. It starts from here. It starts from here and it goes like this. It peaks actually somewhere here and then drops off like this. Something like this, okay? And it actually peaks at around 700-800 nanometer. And actually it looks much more, decays much faster and then drops off sharp, and then here again it drops off sharp. So the difference in silicon between green and red is quite big. Okay? And on top of it, it is much easier to make LEDs and lasers in red light than in green. Remember, when LEDs came out, first they were red, then they were green, and took a long time to make them blue. And the same for lasers. When lasers came out, they were first red and infrared, took a long time to make them green or blue, like Blu-ray, DVD, right? So both the light sources are much easier to make in red, and the silicon, this is sensitivity of silicon, actually peaks in deep red or infrared, depending on the diode. So bottom line, all optical sensors you design, you always use red or infrared. And some good numbers are 830 nanometers, 950 nanometers, and sometimes 780 nanometers. And if you really want to see the spot, because all these are invisible wavelengths, right? You want to see the spot, so it's important to you to see the light spot and know what's happening, then you use 650 nanometers, which is laser diode. So these are like, the reason I'm saying these are the best frequencies, because the industry standardized more or less. There is no theoretical reason. It's just industry standardized that you can buy a lot of lasers and detectors optimized for these wavelengths. There is a history to it. The history to it That was the wavelength of the original CD player. So the world was flooded with cheap laser diodes at 780 nanometer. Okay? That was the wavelength of the original high-power lasers. So the world was flooded with this wavelength. 950 is a standard of all IR remote controls, garage door openers, video games, everything which has a optical remote control works at 950. So if you pick another frequency, you wouldn't be able to buy filters and you wouldn't be able to buy cheap components. So it's better, since it doesn't really matter, the silicon is pretty flat in this region, it's better to pick one of those 4 wavelengths where the cheapest components are available. And the filters, of course, you want to find a filter like this. Matter of fact, if you go at 950, the photodetectors already have this filter built into them. Because everybody who makes the photodetectors realizes that the customer an hour later will phone back and ask if do you have a filter for it. Okay, so they already put the filter in, so when you phone back they say don't worry, it already has a filter. Okay? So this is actually one of the better frequencies because the detectors already come with a filter. But it's not visible, so it's a problem. And so if you want it visible, use this. Good. Okay, is there anybody here who didn't understand or want me to explain again this issue of the double filtering? Filtering for the frequency of the light or the color of the light, and then filtering for the AM modulation, for the AM carrier. Clear? Good, we'll move on. Now the next class of optical sensors are digital optical sensors, because right now all the sensors I described have an analog output. The output is more or less linear, it's proportional with a variable. But the disadvantage of an analog output that, let's say if you wanted a 1 meter sensor with a 10 micron accuracy, you would need linearity of 1/1000%, because 10 micron in 1 meter is 1 to 100,000. 1 to 100,000 is 1/1000%. So you can realize that if you want very large ranges with very high accuracy, there is a problem with analog sensors because you are not going to be able to get the linearity. Typical linearity of an analog sensor is 1%. And if you really do your homework, you get to 0.1%. If you do everything carefully, you don't saturate the sensor, differential, normalized, all the tricks in the book together, you get 0.1%. But that's about it. Because of imperfections, it's hard to get an analog sensor to 1/1000%. So obviously you have to move to some digital sensor where you have a thing like a counter, which each micron you move gives you a count. Okay? And these things are called optical encoders. All of you have seen them because I know in your projects you use things like this. And they work, and they are also distance sensors, which could be made into angle sensors. And as I mentioned many times, if you have a distance sensor, you can convert it to a force sensor, pressure sensor, anything sensor. Okay? So optical encoders are simply scales. They have lines. The lines are very closely spaced, and you have a detector which counts lines. So an easy way to do such a detector is, say, if you have a light source, like a laser, and you focus it. You have a laser and you focus it, so you already know now if this will be 1 f away, I'll get a very small spot. Then it will keep expanding again. Then I put a detector here. So as I move what's called a grating or a scale, it will chop the light. The black will stop it, the white will let it pass. So if I move this, I'll get a square wave here coming out of the detector, and then I can just count pulses. Okay? So all of you have seen those on motors and robotics and everywhere. But like everything else, like in all the previous sensors, there is a good way to do it and a dumb way to do it. Okay? sad to report that most rotary encoders you can buy are actually done the dumb way. And I'll explain why. But anyway, but they're good enough. Okay. So let's start with this. So the basic optical encoder is, we'll turn this on. Oh, it's on. Okay. So the basic optical encoder is some scale. Okay. And I just shine a laser through it, and I move the scale, okay, and I can show it here. I move it, put in front of the laser, and I move it. You can see the modulation. Let me, probably don't see it. Where is the, what's going on here? Why don't I see the spot? Oh, it's too bright. It saturates the camera. See, it doesn't show the spot, but you can see the. Maybe if I'll put something dark, the camera will see it, because the white saturates the camera. We talked about saturation of sensors. You see a good example that this is 1,000,000 times brighter than this, but the white already saturates the sensor. So now I should be able to see it. Yes. See, a good demo of saturation of silicon sensor. Okay. Now, okay. So this is a spot, and now I'll run the grating through it. You'll see it being modulated. You see, guys, it goes lighter and darker as I go through it. You don't see it much because it also saturates. Even the black has enough light to saturate, so you don't see it going fully out. But anyway, well, you get the idea. Okay, so you just move the scale here, and the scale chops the light. You have a detector. You count how many pulses. You're done. Okay. So now, yeah, it's actually quite amazing that this is just normal white, and it shows so well, and it cannot see the laser spot at all. See? Because it's totally saturated with the white. Okay, so now, if I want a rotary sensor, like a angle encoder, it's the same thing. I put a disc like this, I put a laser, which I can see again, shining here, and when this rotates, it modulates the light behind it, which I can't see, but I can see it here. I can see the reflection. It's good enough, black and white. You see, it modulates the reflection. When it hits the white, it reflects more. Okay. Now, this doesn't help much, or this has a problem. And one problem it has, I don't know if I'm going left or right, because all that I'm getting when I'm turning this in the laser, all that I'm getting is I'm getting pulses. But when you get the pulses, if you reverse direction, you still get pulses. So the first thing I need is a way to tell if I'm going left or right. And does somebody know how this is done in optical encoders? Or in all encoders, actually, not just optical. How do you know which direction you are turning?
Use a quadrature encoder.
Pardon?
Use a quadrature.
Very good. So does everybody know what quadrature encoder is? Is there anybody who doesn't know? Because I know you don't respond. Okay. Good. Okay, so I'll explain it quickly. If you had on the same disk two sensors, one sensor lined up with a black line, and one sensor lined up 90 degrees apart. 90 degrees meaning a full cycle I call 360 degrees. So I will have a sensor which is not lined up on the white line, because that will be 180 degrees, but lined up on the transition between black and white. So this will be 90 degrees shifted. So again, these are the lines. These are the black lines and white lines. So one sensor is aligned on the black line, and the other sensor is aligned not on the white line, but on the border, which is 90 degrees in the pattern, shifted, and because of that it's called quadrature. Quadrature in electrical engineering means 90 degrees. Okay? So the second signal will be like this. It's the same as the drive waves for a stepper motor, for the same reason. You know, it works with quadrature. So now I will be able to tell the direction, because if I'm going one way, if I'm going with the grating one way, this will be leading. It will be like this. This will come ahead of this. Because if I move the grating this way, this sensor will be hit first. Now, if I go the other way, if I reverse direction, this sensor will be hit first by the bar. So the pattern will reverse. It will be like this. Okay, so this is the waveforms I get when I go this way, and these are the waveforms I get when I go this way, because again, if the round circle is my detector, if I go this way, this detector sees the pattern first. If I go this way, this detector sees the pattern first, so the phase of the waveform reverses. Okay? And because they are not, if they were 180 degrees, I still wouldn't know anything. Because when I reverse it, they still look 180 degrees. But if I do it 90 degrees, and I call this the reference. If I call this the reference, 0, this waveform will be called 90, this will be called 270. Because it's shifted in the other direction. Okay, it will be like this. Okay, it doesn't, by the way, it doesn't have to be 90. If I did it 10 degrees apart, it would be just as good. Right? Because if I have two sensors which are just shifted 10 degrees on the pattern, I will have the same information. If one is leading, it's going one way. If the other is leading, it's going the other way. 90 degrees is just a nice number which is useful to drive motors. But in encoders, any shift between the detectors will be able to tell me the direction as long as it's not 180, where then it looks the same. Clear? Okay. And there's a standard logic circuit which decodes that to tell you direction, and you can actually buy this in a chip. You can make your own logic for a few gates which decodes, but you can also buy a chip which is called, it's basically a shaft encoder, a decoder, which gives you give it A and B, and it outputs an output which says pulse and direction. And all it does, it checks which is first, which is first. Okay? Good. Now, you need another thing in order to orient yourself when you turn on the power. A shaft encoder like this, wherever you turn on the power, wherever you leave it, will show you the same thing. So you need something called an index or a reference mark which tells you this is 0. So from 0 you can start counting. So you can do it two ways. If you have a machine, let's say you have a machine tool, and the machine tool is driven by a lead screw with a shaft encoder. Here there's a motor and there's a shaft encoder. Okay? Now you can have a reference mark here. You can have an optical sensor here, which is called reference. And when you start up the machine, it moves in one way until it hits the reference, and it knows it's 0. Now from this point, it just has to know which direction and how many pulses. So once you have a reference which is 0, if it goes this way, it counts up. If it goes the other way, it counts down. It's connected to what's called an up-down counter, which is a chip which counts up or down depending on the direction command. So one way to get the reference is from the machine itself with a sensor which is typically what I showed you as a split detector position sensor, because that's an excellent null sensor. It's immune to noise, immune to everything. If you put a laser diode here and a split detector here, you can pick up the null to a micron easily. And if you don't like the laser diode here, you can do it with a mirror. You can do it, in other words, if you don't like wires having to go to a moving part, by now you're clever enough to know how to do it with mirrors and so on, that all the sensing is on this side, all the electronics is on one side. So one way is just use an encoder like that, no reference, and use a reference here, which is just a separate sensor which tells you 0. Now most people prefer the shaft encoder itself also to give you 0, and for this you add a detector which is called an index detector. So one of the lines, all these lines are the same, but one of the lines is different. And you pick this up with a separate detector, and when you hit this line, you know that's a reference. Okay? So now, if you take apart the shaft encoder, you find out that a lot of times they don't want to use a laser, they want to use an LED, and an LED cannot be focused that well. So you find out that the way they make the detection is instead of shining a single beam through it, they actually have a little thing like this which has several lines. And what this does, if you put it over this, it just increases the sensitivity. When I turn it a bit, it goes all black, this area, and I turn it a bit more, it goes all white. Actually, I should turn this. And then again, I turn it, it goes all black, and then it goes white. So what this allows me to do, it allows me to use a light source which doesn't have to be focused so small, right? Because now I can have a light source which is this big, rather than here where I needed a light source smaller than a line. So if you use a laser, you can shine it between the lines. But if you use an LED which is big, you do this trick, and now the whole area goes dark. Okay? And if I want to pick up the index or the reference, I have another line here. It will look something like this. I will have another set of lines sticking out somewhere here, and I will have a separate sensor for this, for the index. So typical shaft encoder, when you buy it, when you look what comes out of it, the shaft encoders look like little motors. Look like this, have a shaft. And typically they have 3 lines coming out of them besides power. They have power, let's say 12 volt, and then they have A, B, and index. So if you look at the connector, typically it has 5 wires. A is versus ground, right? One of those 2 wires is ground. It's either 5 volt or 12 volt, whatever. So this is ground, which is also ground for those. So versus ground, you get A, you get B, and you get an index. And the reason you need A and B again is you can connect it to a decoder chip to tell you the direction. Is that whole story clear? Good. Now, same thing is for linear encoders. Exactly the same idea. So you have a linear encoder. A normal decoder will be a slit like this, and it's moving under, let's take this away, it's moving under the slit, and here you can see nicely, if you had a light source, the slit was a bit narrower, you could see black, white, but it would be better if actually the slit was a bunch of lines, and then you get something like this, which the whole area goes black or white, but because the AGC on this camera, you don't see it well. You have to line them up like this. Okay, so the whole area goes black, white, so you don't need a small LED or a small detector. Okay, that's how you do it. By the way, when I tilt it like this, I get some bands running through it. See, I get some bands running up and down. Okay, what are they called? What is this effect in physics called? When I line up 2 patterns and then I move and I see these bands running. I see like a different pattern appearing, which is horizontal bands. See, I have different pattern appearing, and I can make them very wide and running up and down. But basically these are vertical, but when I put them together I get some horizontal pattern. So what's that called? It has a name. Moiré, very good. That's called moiré, and okay. And who was Moiré? There's no Moiré. Moiré, it's named after some fabric. There was no Mr. Moiré, or maybe there was who invented the fabric, but it's just named after a fabric. Like that. Anyway, so or maybe there was, maybe I won't. But anyway. So, moiré is this pattern. Now this pattern is actually very important because, as you could see in this simple demo, it allows you to magnify the motion. Because if I do a moiré pattern and I come at a very shallow angle, if I move the films like one line, the moiré pattern will move a lot. So I can get any magnification I want of the motion. Like here, say it's roughly 1:1. But if I go to very shallow, the slightest movement will shift the moiré a lot. So this is a very good optical amplifier, because I can put photocells in the other direction and count the moiré instead of counting the lines. And I'll get a much amplified motion, right? So that's very useful for sensitive detectors. Matter of fact, there's a guy by the name of R.V. Jones, and he is famous for other things. He's a fellow who discovered in World War II that the Germans use radio beams for navigator bombers. So he wrote a book, A Man Called Intrepid. Anyway, he was both a physicist and also worked in intelligence in World War II. He wrote a very good book which UBC library had, I don't know if it still has, called Experiments and Experiences by R.V. Jones. And he died recently. And in his book, he shows some examples of amazing sensors that he built. So he built one sensor using a combination of Moiré and optical sensing and so on that could measure a movement of a thousandth of one atom. And he showed demo examples in the book. If we have time at the end of the course, we are going to cover some unusual sensors, and I'll bring in some material about this sensor. But using this Moiré to amplify the motion plus electronic amplification, he could measure a thousandth of an atom. For example, if he took a piece of metal, he could measure if it heated up by a millionth of 1 degree. Because a millionth of 1 degree moved at about a thousandth of an atom, and he could measure that clearly. Anyway, so just to show you the power of well-designed sensors. Okay, so this is Moiré. You know, it's very useful in sensors. So this is how you build detectors. So we covered the basics of shaft encoders, but let's talk a little bit about the finer points, because what I covered here is a standard description of shaft encoders, but now we get it a little bit into the finer points. So it's not difficult to make a perfect disk with perfect lines. So when you start thinking about what limits the accuracy of encoders, I can make a perfect disk with perfect lines divided to an accuracy of as low as 0.1 arc second, which is quite amazing that you can do that. But you can actually buy a disk divided to 0.1 arc second. All of you have seen this disk. Pardon? CD? No, CD is not divided to that accuracy. It's plastic. The CD has lots of little dots, has 1 million dots in the circumference, but the accuracy is not nearly that. It couldn't be. It's just made of polycarbonate, you know. But somewhere when you walk to university, you see somebody holding this disk divided to 0.1 arc second, which is astonishing accuracy. Yes? Pardon? Watch? No, watch is... Why would a watch be divided to 0.1 arc second? No. So, it's actually the only time in your life you'll see such a thing, because nothing else you'll ever see has this accuracy in terms of division. So, have you ever seen surveyors at work? I'm sure you've seen surveyors at work. One guy holds a stick and the other guy looks through some telescope. That thing that the other fellow looks through is called a theodolite. Theodolite is something which looks like this. It has a telescope. It sits on a pivot, and the base sits on another pivot. So it can measure this angle and this angle, alpha and beta. So you turn it this way and you turn it this way. Okay? Now these theodolites, the regular ones are good to 1 arc second, and the really good ones are good to 0.1 arc second, which is astonishing. If you really think what it means, astonishing, because remember, 0.1 arc second, let's say 0.2 arc second is 1 microradian. 1 microradian is if you go a kilometer away, okay, you look at something a kilometer away and you move it up 1 millimeter, you change the angle by 1 microradian. So a theodolite will be able to pick up if a person is standing a kilometer from you and that person steps on a newspaper, which is 1 millimeter, in the theodolite you can measure the difference. So that's no joke. It's not so simple. So how does so this is just proof that you can buy disks at a reasonable price with perfect accuracy. Okay? So where is the source of error? So you start thinking about it and you realize right away, if you have a perfect disk, you still can have an error, because when you mount the disk on a shaft, there would be eccentricity. Nothing can be perfectly mounted, and even if it's perfectly mounted, the shaft itself, when it rotates, doesn't really rotate around a fixed point, because there is something called trueness of rotation. So even a ball bearing, when it turns, the ideal point of rotation is drifting. So in a ball bearing, the balls come in and out. Each ball is a bit different. So nothing is perfect in the bearing. So, and also when you mount the disc, it's not perfect. So what happens if you have a detector here, okay, and this is eccentric. Eccentric meaning, let's say the disc is mounted like this, with some eccentricity, which we'll call epsilon. That's eccentricity. So when you're measuring here, and the disk is rotating around this point, okay, at one part it'll seem to be moving faster, and at this part it'll seem to be moving slower because the radius, okay, so the radius, this will be r minus epsilon, this will be r plus epsilon. Is that clear? So take an extreme case. If this is a disk and it's rotating around this point, and these are the lines. So when you look here, when you have a detector here, and this is epsilon, clearly this is r plus epsilon, and the lines will pass faster. While if you switch 180 degrees, here the lines will pass slower because the radius is shorter, so you'll get an error. Okay? And you can see right away that the error is proportional to epsilon over r. The error is epsilon over r. And you get plus this error and minus this error, okay? Because it's proportion. If you make r bigger for the same epsilon, the effect will be less. Good. So how does a theodolite get rid of this problem? And that's how all high precision encoders get rid of this problem. When you buy a normal encoder today, the limit of accuracy is this mounting. Because all the encoders you have seen, the encoder itself is much more accurate than the way you mount it. Because the way people mount an encoder, let's say, if you look at typically what people do with an encoder, they either take the encoder, connect it with some timing belt, and of course the pulley of the timing belt has run out. And this has run out, everything is run out. So this limits the accuracy right away to maybe 20 or 50 arc second. So some other people say, no, we wouldn't use a timing belt, we'll take the lead screw, this is a lead screw, put some coupling here and connect it direct to the encoder, but of course this coupling has run out. So basically all these things, all the normal encoders you have seen and the way you mounted them, that limits your accuracy to many tenths of arc seconds. But if you want to get down to measuring things to a few arc seconds, you have to see what people did in a theodolite, and then you realize what to do. So how does a theodolite get rid of this problem? That's an invention from hundreds of years. Yes?
Do you machine the encoder in the shaft?
It's hard. In theory, you can make a shaft and then make the encoder on the shaft, but it's very difficult because the encoder is a piece of glass made by printing the way you make silicon chips. Because the lines are very fine, you can't machine them. Right? The lines in a theodolite or in a good encoder, they are 10 micron wide. It's hard to machine them. There's thousands of lines here. So you have to make it on a glass disc and then mount it on a shaft. But even as a shaft itself, the bearing can have some run out. So theodolite has the best bearings, the best glass, the best everything, but still not good enough to 0.1 arc second. So again, just to explain to you what 0.1 arc second means, 0.2 arc second is 1 millimeter over a kilometer. So if the encoder was a meter, it would be 1 micron. Because the encoder is only 10 centimeter, it would be 1/10 of 1 micron accuracy. So it will be like 1/5 of a wavelength accuracy in mounting the disk. That's where the difficulty comes. You follow this calculation? If I'm talking about 0.2 arc second, the eccentricity on a 10 centimeter radius encoder has to be 1/5 of a wavelength of light. That's tough. Yes?
Should we measure from both sides?
Ah, that is a very good idea. See? Did you think of it or did you know about it before? Pardon?
I
actually thought about that.
That's good. So you see, so that's a very good sign. Okay. So what you do is you say at this point it's R over E, at this point it's R minus epsilon. Why don't I put two sensors? I take the disk and I put two sensors, one here and one here. And these are the lines. And then what I do is I average them, because the errors are very small. The errors are less than one line. So if I go here, if I look what's coming out of the sensor, I get a sine wave. When I look what's coming out of that sensor, I also get a sine wave, but at times the sine waves will shift a bit. One will look like this, but it will still be the same frequency because I exaggerated here the error. The actual error, if these lines are 10 micron, typically 10 micron wide, the eccentricity is typically 1 micron. So what we really get, you'll get a sine wave which is shifted by maybe a tenth of the sine wave. So the errors are not big because you're trying to make it as accurate as you can. So what you do, you add up the two sine waves and average. So if you take this sine wave and this sine wave, now you probably know from physics, when you have a sine wave and you average it with another sine wave which may be slightly different in frequency, momentarily it's slightly different frequency, when you add them together you'll get a sine wave which has the average of the two. Like you'll get this, but the frequency of the new sine wave will be the average of the two. Okay? So if one frequency f is proportional to r plus eccentricity, the other one, this is f1, this is f2, is proportional to r minus eccentricity. If I do f1 plus f2, I get something proportional to 2r, because eccentricity cancels out. And you only need 2, you don't need 4 or 6. The moment you have 2, because eccentricity has a nice property, whenever it's maximum at one end, by definition is minimum at the other end. And in between, it's some value in between. So when you go to the next level of encoders, like in theodolites or so on, you measure both ends and average. The way the theodolite does it is very cleverly. It superimposes these two optically, one on top of the other, because the old theodolites didn't read out electronically. You just looked through an eyepiece. So what it did, it had a mirror here which took this picture and superimposed it on this picture. So in other words, what the theodolites did, they actually took the scale from both ends of the disk and superimposed them visually. And then you saw one scale which was a little bit wider or different, and then you had a cursor, you took the center reading. Now outside here, right outside this room, there is a display case full of theodolites. So now when you walk by it, you'll have more respect. Okay? Good. So this is how you fix eccentricity. And this is the main source of error in encoders. Yes, please.
How do you make sure all of the marking lines are very accurate?
How you do that? Okay, that's a very good question. It's actually worth a few minutes of the lecture to explain. And then okay, so how did you make the first disk which was so accurate? Because once you have one disk, you can copy it, just like you copy contact print films. You take the disk, take another piece of glass with some light sensitive emulsion, put it down, put light on it, and it'll copy, and then etch it. The way chips are made and so on, or the way printed circuit boards are made today. But how did you make the first disk so accurate? So, yeah, does somebody know?
I guess.
How?
You make it very big and then reduce it.
But how did the first disk, even big, how could you make it accurate to 0.1 arc second? When you reduce them, by the way, strangely enough, the accuracy doesn't improve. Because angular accuracy doesn't improve with size. Right? Linear accuracy would if you could reduce it. But strangely enough, if you make this big a disk at 1 arc second error, you reduced it optically to this big, it's still 1 arc second error. Okay, but it's what you said is true for linear scales. So, but how did you make the first disk to 0.1 arc second? So, the way you make it is there are some patterns which are self-checking. For example, if you want to make a right angle, and you have no way to verify it, it's still self-checking, because you can make two of them, and make sure they're identical, and then put them side by side and make sure they create a flat line here. Okay? So some patterns, there's many examples of patterns which are self-checking. Okay? So you don't need a reference to do them. Now, turns out the division of a circle is self-checking. So because when you divide a circle, okay, at the end, let's say at the end it has to close. Because if you start from 0 and you have a machine which divides it, it scribes. First of all, at the end, the last scribe has to close, because it has to be 360. But more than that, if you put, say, 4 microscopes here, the microscopes don't have to be placed at exact positions. Just randomly placed 4 microscopes. Each one has a crosshair. And if the circle is perfect, when you line up the 4 microscopes, that the crosshair lines up with an encoder line. Now, any position where 1 microscope lines up, when you rotate the disk, all microscopes have to line up. Because if in the initial settings, these were the lines, and in the initial settings, and these are the crosshairs in heavier lines. So if the initial settings, the crosshairs lined up with the reticle lines, okay, then at any other position, if 1 microscope lines up, the others have to line up. Because they are all multiples. All the microscopes are set at multiples of reticle lines. It doesn't have to be 90 degrees, but it has to be multiple. So if this is delta theta, a reticle line is delta theta, this has to be n delta theta, where n is an integer. And this is m delta theta. Okay? Now, if the division is not perfect, when you turn it a random angle and line up, the others will not line up. Okay? So you can note the angle. And then you can start moving the lines a little bit until at any position all 4 microscopes line up. Only then it's perfectly divided. And because it's closure, if it's perfectly divided, it will add up to 360 and everything is correct. So did everyone understand the trick? Okay? The trick is based that all these are integers originally, and if the division is perfect at any position of the disk, they have to line up, and if they don't line up, you can measure the delta, the small error, and then you can move the line a bit and move the line a bit until they all line up. Okay? And the way you do it originally, you make a gear and you file the teeth. So what you do is you make a gear, and what you're trying to get is the teeth to be equally spaced, but the teeth can be filed a bit with a file, so you keep correcting the teeth until all microscope read all positions, and that's how, and you can keep doing it, and because this is magnified 1,000 times, you can get it very accurate. So you do start with a big gear, because now you're dealing with linear positions on the teeth. So you start with a 1 meter gear, and you lap or file the teeth until it lines up in all positions, and you can get to this accuracy. And who is the first guy who figured it out and did it? His machine is in the Science Museum in London. Ramsden. That's very, very, very important. And why? And this was 200 years ago, more than 200 years ago. And why was he so keen? Why was he so? He didn't build encoders 200 years ago. So what was the most important thing to Britain 200 years ago? Compass, yes, but compass doesn't need this accuracy because the magnetic field of the Earth is not that accurate. But there was something else besides the compass which was the most important thing to Britain 200 years ago. Pardon? I can hear you. Clocks, yes, but that was a different guy. Yes, that's true. To navigate you need a clock, and that was also done 200 years ago by John Harrison. That was a marine chronometer. But that's not this. Yes?
Artillery, maybe?
Getting closer. Okay, so the most important thing to Britain 200 years ago, besides the clock, which is true, because there was a sextant. Because the way you navigate on the ocean, because Britain ruled the colonies by its navy, and the navy needs two things, a sextant and a clock, to know where they are. because a compass is good too, but not accurate enough. So with a sextant you can measure the position of the sun and the horizon and so on and figure out the local time. And with a clock you know the Greenwich time, and if you know the difference, you know your longitude. Okay? And with a sextant you can also get your latitude. So basically you need two things, a clock and a sextant. The clock didn't need this, but a sextant is actually a shaft encoder, like a theodolite. And you can see it also behind this wall in the cabinet, right? So a sextant, even an old sextant from 100 years ago, is accurate a few arc seconds. So they needed a machine which makes encoders. And Ramsden made this machine, took him a year of lapping, and there was a big success. And the amazing story that during World War II, suddenly the British needed a lot more sextants because of the war of the Navy, and they had a machine which makes them, but very slow. And there was a desperate shortage. So some fellow remembered the story of Ramsden and this machine and went to the Science Museum and asked to borrow Ramsden's machine, put electric motor on it. It was driven by hand, because after it was calibrated it could cut sextants automatically. You turn the crank and it would cut. And he just put a little electric motor on it, and he cut a few thousand sextants in a week. And he was knighted for that. He was knighted for remembering that that machine in the Science Museum, which was sitting there 100 years or more, is accurate enough to cut these sextants. Okay? So that's a history of how you divide the circle. And so I'm glad you asked, because it's a nice story. Okay, so we can make the encoders accurate, we can cancel the eccentricity, but there is still something that I'm surprised nobody does, which is very effective. And what you can do, you can make a different encoder where you just put two disks together, one on top of the other, and one disk is rotating and the other one is stationary. And what you do is you average the light over the whole disk. So if I line it up accurately, if the whole disk is this, you get all black, and if you move, the whole disk gets all light. Okay, so if you do that, if you have two glass disks, one stationary, one rotating, and you have a big LED shining on the whole disk, this has major advantages, because first it takes out eccentricity, because you automatically average from both ends. But it also gives you an average of all lines rather than looking at one line or a few lines. Because if the residual errors are random, which they are, because you do the thing with the microscopes on the master until you can't correct anymore. So if you have in a disk 10,000 lines, which is typical on a high precision encoder, and the errors are random, and you average the whole disk by what you learned in statistics, you reduce the error square root of n, which is square root of 10,000, which is 100x. So you're actually improving the accuracy 100x if you did that. And to my surprise, nobody does a commercial encoder like that, but you can buy a mechanical encoder like this, because there is something called a dividing head, which is like a mechanical encoder used in machine shops and metrology. And they actually work like that, by averaging all they are gear with many teeth, and they average all the teeth. So I'll talk for a few minutes about it next week. But that thing indeed is accurate to 0.1 arc second. And that's the most accurate thing in the world. That's what the bureaus of standards use. And it's just two gears instead of lines on a disk. It's just two gears meshing together. And you can mesh them, but when they mesh, they average all the teeth. Okay? That's called an ultradex. And it's quite an astonishing device, which is the most accurate thing in the world and used by the bureaus of standard. Okay? So anyway, I'll talk about this and talk about the index, but it's surprising that this simple thing of averaging two disks together, there is no commercial product, and this would improve accuracy by 100-fold. Okay, that's all for today.